Welcome. This is Coach Dorff. We're in section 5.3b, and we're looking at some homework examples. In all these examples, we're going to be evaluating integrals. So part A says we have this integral from 1 to 4 of x to the negative 1/2 dx. What we want to do is to find out what is the antiderivative of the integrand, the antiderivative of this function right here. All right, that's the integrand, the function that's after the integral sign. Well, remember earlier when we talked about finding antiderivatives, if we have a function, if we have x to some power, then what we do is we add 1 to the exponent, and then we multiply by the reciprocal of the new exponent. So I'm going to take x to the negative 1/2, I add 1 to that, and I'm going to get x to the positive 1/2. And now my new exponent is 1/2, so I multiply by the reciprocal of that, which is 2 over 1, or I can just write that as 2. And then I have my plus c there. So this is the antiderivative of x to the negative 1/2. So how do we use that in solving this problem? Well, what is an antiderivative? So recall that an antiderivative would have the property that if I took the derivative of the antiderivative, I'm going to get the original function there. So in this case, if I take the antiderivative of 2x to the 1/2 plus c, I get x to the negative 1/2. So what I can do is then I can start with my original function, integral from 1 to 4 of x to the negative 1/2 dx, and I can replace that integrand function with the derivative of 2x to the 1/2 plus c. Now that may look like I've made the problem more complicated, but now here's where the fundamental theorem of calculus comes in. Notice that I have the integral of a derivative. What does the fundamental theorem of calculus tell us? It tells us that if I have the integral of a derivative, they undo each other, and I get the function that I started with. So in other words, what this is going to equal is this inside function here, 2x to the 1/2 plus c. All right. Again, when we looked at the fundamental theorem of calculus part 1 in the previous section, in that case, we were doing derivatives of integrals, and then we had the integrand function. And then we could solve that because of the fundamental theorem of calculus part 1, because the derivative of integrals undid each other. Here, we're taking our integral and we're writing the integrand, the inside part, as an antiderivative, and we have the derivative of that antiderivative. So we have an integral with a derivative, they undo each other, and we get this. Now, what about these limits on the integral sign here? Well, we're going to use those, and we're going to say we're going to evaluate this function from x equals 4 to x equals 1. And where do those 4s and 1s come from? Those are these limits here. That's where I get those from. So we keep working on this problem here. What I do then is I put in x equals 4 for x, and then I put in x equals 1 for x. And I take those results and I subtract them. So then I get 2 times 2 plus c minus 2 times 1 plus c, or in other words, I get 4 plus c minus 2 minus c, and I end up with 2. Now, there's one thing I want to point out here. What happens to the c in this process? It cancels out, right? Because one of them is going to be a positive and one will be a negative. So they cancel each other out in this process. So often when we solve these types of problems, you don't have to put that c there because it's going to cancel out automatically. Every single time it will cancel out. So I could have just said, instead of finding the most general antiderivative, 2 times x to the 1/2 plus c, I could have found any antiderivative. And in fact, the easiest one to take is the one where c equals 0. So in this case, the easiest antiderivative would be 2x to the 1/2. All right. Also, one last thing I want to point out is, remember that integrals represent the area under the curve. So what does this curve look like? Originally, we had x to the negative 1/2. That curve looks like this. This is the function y equals x to the negative 1/2. At the point x equals 1, we have y equals 1. So we have the point 1, 1. And at the point x equals 4, we have the point y equals 1/2. So we have 4, 1/2. So I can think of the integral here as this area under the curve. So that area, which equals the integral from 1 to 4 of x to the negative 1/2 dx, is that blue area there. And we know, because we just solved the problem, that that area is equal to 2. And that makes sense because it's above the x-axis and below the red curve there. Now, let's look at another example here. All the examples will follow the same pattern. What you need to do is you're going to have an integral of a function, and you need to find the antiderivative of it. In the first problem we did, it was fairly easy to find the antiderivative because we just had x to the negative 1/2. Let's look at some other examples of integrals where it's a little bit harder to find the antiderivative. It's not so obvious. So the second example, let's look at the integral from 1 to 3 of x cubed minus 2x squared minus x all over x squared dx. And we want to find, again, what are we trying to do? We want, what is the antiderivative? It's the antiderivative of this here. Well, in the form that it's written, I don't see really easily what that antiderivative is. So what I'm going to do in this case is rewrite it. So I've got x cubed minus 2x squared minus x over x squared. And I can rewrite that by putting each of the terms in the numerator over the denominator. So I have something like this. And now I can simplify those terms to be x cubed over x squared is x minus, now I have 2x squared over x squared, so that's minus 2. And then I have minus x over x squared, which is minus 1 over x. So now I've rewritten my function to look like that. And so then I ask myself, what's the antiderivative of this function here? Well, it's much easier to find the antiderivative of that. So what is the antiderivative of that? Well, now I can use the anti-power rule or reverse power, I don't know what you want to call it. The same rule we used when we tried to find the antiderivatives of functions with exponents. So the antiderivative of x to the first power, I'm going to add 1 to the exponent, so I'm going to get squared. And then I multiply by the reciprocal of that, so I get 1/2 x squared. So that's the antiderivative of x. Then I've got minus 2. What's the antiderivative of minus 2? Well, that's going to be minus 2x. I can check that by taking the derivative of 2 minus 2x, and I get minus 2. What's the antiderivative of 1 over x? Well, if I wrote that as an exponent, that would be x to the negative 1. If I added 1 to that, and then I would get x to the 0, and I would multiply with the reciprocal of that, that wouldn't make sense because I'd have a 0 in the denominator. This is the one special case where you have x to some power where you can't just do that rule that we did there. Whenever you have 1 over x, or if you have x to the negative 1, the antiderivative of that is just the natural log of x. So we're going to use that. So we note that because it's the antiderivative, we note that x minus 2 minus 1/2 equals the derivative of 1/2 x squared minus 2x minus natural log of x plus the c. But again, I said we don't have to find the general case. We just have to find one case. And in this case, we'll just use where c equals 0. Because if we use, as just like in the previous example, if we put any other value for c, when I evaluate it at my two terms here, where x equals 3 and x equals 1, the c's will cancel out, or whatever constant I pick out will cancel out here. So we've got here this. So my original integral from 1 to 3 of x cubed minus 2x squared minus x over x squared dx is going to equal the integral from 1 to 3 of x minus 2 minus 1 over x dx. And that's from simplifying it like we did earlier. And then I've got that equals the integral from 1 to 3 d dx, 1/2 x squared minus 2x minus natural log of x dx. That's using the antiderivative there. And now we use the fundamental theorem of calculus because I have an integral of a derivative, so they cancel each other out. So I have 1/2 x squared minus 2x minus natural log of x. And I'm going to evaluate it from x to x equals 1. So I plug in 3. I've got 1/2 3 squared minus 2 times 3 minus natural log of 3 minus, remember when I do this, the middle term, I'll do a subtraction between the first and the second term. And now I do 1/2, and I replace the x with a 1. So I have 1/2 1 squared minus 2 times 1 minus natural log of 1. Let's simplify this. I get 9/2 minus 6 minus natural log of 3 minus 1/2 minus 2. And then what's the natural log of 1? Natural log of 1 is 0. So then I have 9/2 minus 6 minus natural log of 3. I'm going to distribute my negative to everything here. And I get negative minus 1/2 plus 2, and then I can leave off the 0. And then when I simplify this, the 9/2 and the -1/2 is going to become 8/2, which is 4. So I have 4 minus 6 minus minus natural log of 3 plus 2. That's all just going to equal natural log of 3, and that's the answer. Now, what does the negative sign mean? Is this answer? Remember that the integral represents the area under the curve, and it's above the x-axis. If you have a negative answer, and natural log of 3 is a positive number, so when I put a negative sign in front of it, I get a negative in front of it. That gives me a negative number. That I have more area below the x-axis than I have above the x-axis. And this is true if I were to graph this function here. It's going to look something like this. And so I'm going, the integral's from 1 to 3, and I have more area here underneath than I do here. It may not look quite like it then graph, it looks a little bit more like this. So I have more area below than I do above. And that's why you have a negative number. Let's do one last example here. Again, all these integrals here, what you want to do is you want to find the antiderivative of the integrand, the function that's after the integral sign. In this case, I can't use the anti-power rule because I have a trig function here. So I need to find what is the antiderivative. What is the antiderivative of cosine of this? All right, well, we just need to remember that the antiderivative of that is sine x plus c, but again, I don't need to do the plus c because it's a constant, and the constant will cancel out when I put the terms in there. Just to make sure you all see that, I'm going to just do again one more time. I'm going to put the plus c in there so you see that it cancels out. So that antiderivative thing means then that cosine of x is equal to the derivative of its antiderivative. Now I've got the integral pi over 2 pi over 3 here of cosine x dx. So that's the same thing as the integral pi over 2 pi over 3 of the derivative d dx of sine x plus c dx. And because of the fundamental theorem of calculus, I have an integral. I'm taking the integral of the derivative. They undo each other. So I'm left with the sine of x plus c, and I'm going to evaluate it from pi over 2 to pi over 3. All right, let me just stop for a moment and show you. This is really the beauty of the fundamental theorem of calculus, that you can get this integral and derivative and they cancel each other out. It just makes life in the calculus world so much more beautiful and easy. The last thing I do then is I'm going to evaluate my function here, my sine x plus c, at these two x values. So when I put in the first one, I have the sine of pi over 2 plus c minus the sine of pi over 3 plus c. All right, the sine of pi over 2 is 1, and the sine of pi over 3 is the square root of 3 over 2 plus c. And when I distribute my negative sign here, I'm going to get 1 plus c minus square root of 3 over 2 minus c. And you see again that the negatives cancel each other, the c terms cancel each other out. And so I get the answer 1 minus square root of 3 over 2. All right, so you don't, when you do the antiderivatives here, you don't have to find the most general. You just have to find one that works. And the easiest one to use is when c is equal to 0. And you get this value here. And again, this represents the area under the curve of the cosine function. If I look at it from x equals pi over 3 to pi over 2. And this is a positive number, so I'm going to have positive area. It's going to be above, majority of it's going to be above the x-axis. Hope that helps you. Thanks.